Hello everyone. Today we'll be looking at decay and transmutation. Transmutation you might have heard of before. It's changing one element into another element, and it's what medieval alchemists tried to do all those years ago on their quest for the Philosopher's Stone. So, what is transmutation exactly? Well, as I said, transmutation is the process of taking one element and changing it into a different element. So we can see here an example of taking carbon and changing it into nitrogen. So this is very different to chemical reactions, which change the configuration of atoms in a chemical. So we can imagine, for example, taking hydrogen and adding it to oxygen to produce water. This is a chemical reaction. It is not a transmutation, because on both sides of the equation we have hydrogen, and on both sides we have oxygen. When these equations stop balancing, that's when transmutation is occurring. Unless, of course, you've just got your equations wrong. So transmutations change the atoms of the reaction. It means that we get something like carbon on one side, and we end up with nitrogen on the other side. So transmutations can only happen when the proton number of an atom changes. Remember, the proton number is what gives an atom its element. All carbon atoms have a proton number of 6. All nitrogen atoms have a proton number of 7. So if we want to change carbon into nitrogen, we need to change the proton number. Now this can only happen during radioactive decay. So this can happen naturally for some substances. For other substances, we need to fire neutrons at it until it decides it's unstable enough to decay. More about that later. So radioactive decay is one of 3 different processes. All of them release radiation, but what sort of radiation depends on what process it is. So radioactive substances are isotopes of elements that have unstable nuclei. So some nuclei are stable, some nuclei are unstable. And even in a single element, it can have stable and unstable nuclei, depending on the isotope. So an unstable nucleus can undergo alpha decay, or it can undergo beta decay, or gamma decay. And these are the 3 different types of radiation that I was talking about earlier. So each one of these is linked to a different sort of particle that's emitted from the nucleus. We'll start off with alpha decay. Now during alpha decay, the nucleus emits an alpha particle, and that's what this object over here is. So we can represent it with the Greek letter alpha. Now an alpha particle consists of 2 protons and 2 neutrons, as we can see from the diagram. But hang on, that sounds a little bit familiar. 2 protons, isn't that an atom? Well, indeed, yes, this is the same as a helium nucleus. But it's not the same as an atom, because a helium nucleus in a helium atom tends to have electrons associated with it. An alpha particle doesn't have any electrons. It's just 2 protons and 2 neutrons. So there are 2 kinds of beta decay, beta minus and beta plus decay. Both of them look roughly like this though. During beta minus decay, the nucleus emits an electron, which is odd because we don't generally think of electrons coming from the nucleus. We think of them being separate to the nucleus. So something odd is going on here. During beta plus decay, which as I said is similar to beta minus, the nucleus emits a particle of antimatter called an anti-electron or a positron. Now these are just the same as electrons, except that they're positively charged instead of negatively charged. And if one touches an electron, both of them will disappear. Obviously they're called beta minus and beta plus because the particles in beta minus decay are negatively charged, and the particles in beta plus decay are positively charged. Finally, we have gamma decay. Now, during gamma decay, the nucleus emits a photon, which we can see over here. So unlike the others, it's not emitting a sort of solid particle. The photon is called a gamma ray and has very, very high energy. Now cast your mind back, if you will, to the electromagnetic spectrum, where we went from radio waves, microwaves, infrared, visible light, ultraviolet light, X-rays, and right at the top we had gamma rays. So gamma rays are the highest energy photons in all of the electromagnetic spectrum. So you get a lot of energy coming out from these radioactive particles. So how do you figure out what transmutes into what? Well, we use conservation of mass and conservation of charge. The atomic mass of the nucleus is conserved after decays. We have here an equation of decay, polonium turning into lead, and a helium nucleus, which is an alpha particle. So if we look at the mass of all the particles involved, we have a polonium atom weighing 210 atomic mass units, turning into a lead atom that weighs 206, and an alpha particle, which has two protons and two neutrons, giving an atomic mass of 4. So we can see that we have the same mass on both sides of the equation. The other thing that's conserved is charge. If we look at the number of protons on each side of the equation, or the charge on each side of the equation, we have 84 positive charges here, 82 positive charges, and 2 positive charges. So that means that our charge is conserved. We don't gain or lose any charge during the transmutation. This means that it's possible to predict exactly which substance something will decay into just by knowing what sort of radiation it's emitting. So let's go through them. When a nucleus emits an alpha particle, this is alpha radiation, its mass decreases by 4 atomic mass units, because an alpha particle is the same as a helium nucleus. It has 2 protons and an atomic mass number of 4. Its proton number decreases by 2. So you can see that in this case, we're starting with a proton number of 84 and ending up with 82. The other protons have gone into the alpha particle. The daughter nucleus, the product, will have a different mass and a different proton number. So we can see that both the mass and the proton number here have changed. So that's alpha decay. What about beta decay? So when a nucleus emits a beta particle, its mass doesn't really change. Electrons are so tiny, compared to nucleons, that they don't really make much of an effect on how heavy the nucleus is. So we can see that in these reactions, the mass isn't changing. It's staying at 40 for this, and at 22 for this. However, its charge will change. Now remember, there are 2 different types of beta radiation. There's beta minus and beta plus. So in each case, we'll get a change in the charge of the product, or the change of the proton number, but which way it goes depends on the particle released. So if we look at beta minus, then the electron emitted has a charge of -1. So that means that the proton number of the daughter nucleus will increase. If we add the charges together, we have 19 on this side and 20 -1 on the other. For the bottom decay, beta plus, we have 11 on this side and 10 + 1 on the other. So that means for beta plus decay, the proton number decreases. So the daughter nucleus will have the same mass, but a different proton number. So this is how we can transmute one element to another without it changing its mass. Finally, we have gamma decay, which is a little different to the first 2. There is no significant change in the mass or in the proton number of the nucleus. Instead, the nucleus goes from an excited state, where the nucleus is very excited and energetic, to a lower energy state. Bear in mind that this doesn't affect the electrons, only the nucleus. So this process is usually part of a chain of reactions. So an alpha decay will lead into something like excited nickel, and then that excited nickel will undergo gamma decay to become unexcited nickel. So it's a very important decay, but it doesn't change the mass or the charge of the original nucleus. And once again, just to make sure it's in your head, this has nothing to do with the electrons. We can forget about the electrons completely. We're dealing with the nucleus. This is nuclear physics. So when a nucleus decays, the product is usually unstable. So we start with something unstable, we decay, we end with something unstable. And that means that the new nucleus will eventually decay too. So we can see here, we have something starting with polonium, creating lead. The lead is unstable, so it turns into bismuth. The bismuth is unstable, so it turns into thallium. The thallium is unstable, so it turns into lead. And this isotope of lead is stable. So at this point, the atom will stop decaying. The resulting series of nuclear reactions is called a decay chain, because we can see that all of these reactions are chained together. It's worth pointing out, I think, that we have lead appearing twice, but the first time it appears, when we have lead 211, it's an unstable isotope of lead, and so it will decay into bismuth over here. But when we reach lead 207, this is in fact a stable isotope of lead and will not decay further. So that's the end of the theory. We've gone through all three different types of radiation. Let's quickly go on to some questions. Question 7. What type of nuclear decay is this? Well, we have uranium here, thorium here, and a helium nucleus here. So what does that mean? Well, it's not beta decay, because that's an electron or a positron emitted. We can't see any of those. It's not gamma decay, because there are no gamma photons. And it is nuclear decay, because we are having one atom and changing it into a different sort of atom. So it's got to be alpha decay. We can see that A is the correct answer. And if we remember what alpha decay means, it means that we spit out a helium nucleus, an alpha particle, from the original nucleus. And so that's this part of the equation here. Question 8, something similar. What sort of decay is this, if it's decay at all? So in this case, we're not spitting out an alpha particle, so it's not A. We have carbon-14 turning into nitrogen-14 and an electron. So we have an electron coming out of the nucleus. This is not gamma decay, because gamma decay does not change the proton number. It is a nuclear decay, because the proton number does change. It is in fact beta decay, so B is the correct answer. Beta decay is the emission of an electron or a positron from the nucleus. In this case, it's a negatively charged particle, so it's an electron. Question 9. Complete each decay equation. So we have americium-241 turning into something plus a helium nucleus, which is an alpha particle. So, during alpha decay, our atomic mass decreases by 4 because it goes into the alpha particle, and our proton number decreases by 2 because it goes into the alpha particle. So that means that our new mass will be 237, that's 241 minus 4, and our new proton number will be 95 minus 2, which is 93. So to figure out what element that is, we can look it up on the periodic table. As it turns out, the element with 93 protons per atom is neptunium, a very close relative of uranium. So we can see that on both sides of the equation, the mass is conserved and the charge is conserved. Now a bit more quickly, we'll go through 3 more. B, 233 palladium undergoes beta minus decay. So its mass doesn't change, it's got to stay as 233, and its proton number will increase by 1, so that the charge is conserved. So what has an atomic number of 92? It's uranium. So our answer is 233 atomic mass units and 92 protons for uranium. This is uranium-233. C, lead-209 undergoes beta-minus decay. So its mass doesn't change, but its proton number increases by 1, and it becomes bismuth-209. Finally, we have francium undergoing alpha decay, or francium, sorry. So its mass decreases by 4, and its charge decreases by 2, and we'll end up with astatine-217. We can see that in each of these equations, the charge is conserved and the mass is conserved. All right, question 10. Classify each transmutation as alpha, beta, or gamma decay. So we're trying to figure out what's the missing particle. Start off with, we have A, neptunium-237 into palladium-233. So if we look at the proton numbers of these two, we're actually going from 93 to 91. Sorry, that's not palladium, it's protactinium. And our mass is decreasing from 237 to 233. So if our mass decreases by 4 and our charge decreases by 2, we must be releasing an alpha particle. So this is alpha decay. B, thorium-229 into radium-225. So once again, we'll notice that the mass is going down by 4, and if we look at the proton number of these elements on a periodic table, we'll notice that the proton number is going from 90 to 88. So that means if we lose 4 mass and we lose 2 protons, it's alpha decay. C, radium-225 into actinium-225. So in this case, our mass isn't changing, so we know it can't be alpha decay, but our proton number is. It's moving from 88 to 89. If we're going to conserve charge, it means that we need 88 goes to 89 minus 1, and so we'll emit a beta minus particle. This means that if we look at the number of total charge on both sides, we'll have 88 on this side for the 88 protons, and 89 minus 1 makes 88 on the right side, so charge is conserved. Finally, D, astatine-217 into bismuth-213. In this case, our atomic mass is changing, down by 4, and our proton number is changing, it goes down by 2, so once again, it's alpha decay. Alright, so that's fairly simple. One last question. Question 11. Write a series of nuclear equations showing the transmutation of lead-197 into gold-197. So in this question, we're turning lead into gold, which is exactly what those alchemists tried to do so many centuries ago. So if our mass starts off at 197 and ends at 197, there can't be any alpha decay. We just lose too much mass. So we need a way of changing our proton number so that it's decreasing without emitting alpha particles. So how do we do that? That's right, beta plus decay. So the atomic mass doesn't change, so there can be no alpha decay, but we can use beta plus decay. So we have lead-197 into thallium-197 and a positron. Remember that a positron is the same as an electron, except it's positively charged. Alright, so now we have 197 thallium. What do we do with that? Well, same thing. Thallium-197 turns into mercury 197 plus another positron. And finally, mercury 197 turns into gold 197 and loses another positron. So in each equation, we conserve the charge and the mass of both sides of the equation. Now, it is in fact possible to make lead 197 by taking a different isotope of lead and hitting it really hard with things like neutrons. The thing is, it's so expensive to do and can only be done in such small quantities that it is not economically viable at all to turn lead into gold, I'm afraid. Well, that's the end of the questions. So in this section, we've gone through nuclear decay, alpha, beta, and gamma decay. We've talked about how transmutation can occur and what we mean by chains of nuclear reactions.